In this video, I'll talk about Kirchhoff's voltage law. After this video, we'll have all of the tools that we need in order to analyze electrical circuits. Kirchhoff's voltage law, or KVL for short, is very simple. The sum of all the voltage differences around any closed loop is zero. Another way of stating KVL is that the sum of the voltage rises is equal to the sum of the voltage drops around a loop. A loop is any path through a circuit that has the same starting and ending node. Loops do not, however, have to be physically closed. They can contain, for example, an open circuit, as long as the voltage across the open circuit is accounted for. So, KVL is essentially saying that if we go through a path that ends up at the same node, we have to end up at the same voltage. Now let's do a couple of examples of applying KVL. Suppose we have a circuit that looks like this. There are a lot of different loops that we can define. As long as we start and end at the same point, it's a valid loop. So say I start here and go through these three elements. That's a legitimate loop. We can start here and go through all of these elements. That's also a legitimate loop since I get back to where I started. We can go around all of these and account for this voltage, and this voltage. That's also a loop. Suppose we have a closed loop with n voltage differences around the loop. The voltages are V1, V2, and so on up to V sub n. The assumed voltage polarities are shown. If I sum the voltage drops around the loop going this direction, V1 will be a voltage drop. It goes from positive to negative. Likewise with V2, and so on up to V sub n. That brings us back to our starting point, so these voltages sum to zero. If I were summing voltage rises, I get the same result, just with a consistent sign change on these. At least one of the voltages here will need to be negative. KVL will keep track of the correct sign on the voltages as long as you're consistent about your assumed sign convention. KVL applies to differences in the assumed voltages around a closed loop. In order to make sure that things work out right, you need to make sure you're consistent about your assumed polarities and the signs that you assign to the voltages when you write your KVL equations. In order to make sure you're consistent, I have a recommended approach to dealing with the signs of the voltage differences. You don't necessarily have to follow this recommendation, but it does seem to help people keep their sign consistent. First, always indicate your assumed voltage polarity on the circuit schematic. When writing KVL, indicate the loop on the diagram, including the direction you'll be following the loop. Finally, pick a starting point on the loop and follow the loop you indicated on the schematic. When you encounter a voltage difference, if you see a negative sign first, subtract that voltage. If you see a positive sign first, add that voltage difference. As long as you're consistent with your approach, and all your KVL equations should turn out just fine. And the signs on the voltages you determine will indicate the actual voltage polarities in the circuit. Here's an example circuit. The voltages of all the circuit elements are shown, including their assumed polarities. I can choose any loop I want. For example, let's loop around this leftmost area here and call that loop 1. If I start up here and follow my arrow direction, I see a positive sign first on V2, so I'm going to add that. I see a negative sign first on V3, so I'm going to subtract that. And then I see a negative sign first on V1, so I'll subtract that. Another loop might be over here. I'll go the opposite direction just for fun. The loop direction doesn't matter, so there's loop 2. Say I start up here. I'm going down here, I see the negative sign first on V3. I see the negative sign first on V7, so I'll subtract that. I see the negative sign first on V6, and I see the positive sign first on V5. That brings me back to my starting point, so those sum to zero. In this video, we got the last piece of information we need in order to analyze electrical circuits. Kirchhoff's laws are easy to apply, but you have to pay attention to details, especially your sign conventions. In the next video, I'll do some examples.